Have you ever stopped to think about how your fridge actually keeps your food cold, or how a giant power plant doesn't just melt? Well, the answer often comes down to one amazing piece of engineering. Today, we're going to go on a journey, an engineer's journey, to see how one of the most critical pieces of equipment in our world gets designed from scratch, the heat exchanger.
You might not see them, but trust me, they are everywhere. They are the true hidden workhorses of our modern world. From these massive refineries that give us fuel, to the power plants that light our cities, all the way down to the refrigerator sitting in your kitchen, heat exchangers are constantly, silently moving heat around to make our lives work.
So the big question is, how does an engineer go from just, a blank sheet of paper to a fully functional, efficient, and safe machine? It is definitely not just guesswork. It's a really precise process of math, physics, and a whole lot of smart compromises.
So here's our game plan for this design journey. First, we're going to look at the anatomy, the basic building blocks. Then, we'll dive into the physics of how heat actually moves from one place to another. After that, we'll see how engineers take that physics and turn it into a physical design, before doing a super important reality check. And finally, we'll see how it all comes together in what I like to call the engineering design puzzle.
All right, first up, the anatomy of an exchanger. You can think of this as the designer's blueprint. Before you can build anything, you've got to know what parts you have to work with, right? And you need to know what each of those parts actually does.
I love this Lego analogy because it is just so perfect. Engineers aren't inventing the wheel every single time. They have this standardized kit of parts to choose from, all laid out in something called the Tamiya chart. It's basically a menu of different heads, shells, and ends you can pick from. So the first big decision is just picking the right combo of these building blocks for whatever job you're trying to do.
Okay, so now that we know the basic components, we have to anchor our design on the real world of physics. It's not enough to just pick a shape that looks cool. We have to understand the forces that are actually at play here. It's time to get the numbers right.
So what is it that actually makes heat move? Well, the simple answer is a temperature difference. But here's the trick. As the hot fluid cools down and the cold fluid heats up, that temperature difference is changing at every single point inside the exchanger. A simple average just won't cut it. That's where engineers use this incredibly clever tool called the log mean temperature difference, or LMTD. It is the magic number that gives them the true, effective average temperature difference that powers the whole process.
Now check this out. This is where a seemingly small choice makes a huge difference. You can have your hot and cold fluids flowing in the same direction, we call that co-current, or in opposite directions, which is countercurrent. And it turns out countercurrent is way, way more efficient because it keeps a more even temperature difference across the entire length. And it's not just a hunch. The math, the LMTD calculation, proves it every time.
Okay, we've got our key number, the LMTD. Now we can start turning all these abstract numbers into an actual physical design. This is the fun part, where we start building it on paper, figuring out the real-world size and shape of our heat exchanger.
And the logic here is actually pretty straightforward. It all starts with how much heat we need to move and our LMTD. With those, we first calculate the total surface area we need for the heat transfer. From there, we pick a tube size, and that tells us how many tubes we need to make up that area. And once we know the tube count, we can figure out how big the whole bundle of tubes is going to be.
And this is where the math gets super practical. Engineers will use a formula just like this one to figure out the bundle's diameter. What's so cool is how it connects everything. You can see the number of tubes and their size right there in the formula. But look at that table on the right. Those little constants, K1 and N1, they actually change depending on choices we made earlier, like whether we laid the tubes out in a square pattern or a triangle pattern. It just goes to show how every little decision has a real mathematical impact on the final machine.
But we're not done just because we have the tubes. Just letting the fluid on the outside flow smoothly over them is, well, not very efficient. So to fix this, engineers add something called baffles. These are basically plates that force the fluid to take the zigzag path, and that creates a ton of turbulence. Now, this chaos is actually a really good thing. It makes sure the fluid mixes up and makes much better contact with the tubes, which massively boosts how fast the heat can transfer.
So at this point, we've got a complete design on paper. It looks good, but the huge question is, will it actually work the way we think it will? This next step is the all-important reality check, where engineers have to double back and verify every single one of their assumptions and calculations.
This quote really gets to the heart of what real-world engineering is all about. See, that first design is based on some good estimates.
Now you do a much more detailed, nitty-gritty calculation and you compare the two. The goal is to be within a certain tolerance. You're never going to be 100% perfect, but you have to be close enough for it to work safely and effectively.
So what happens if your calculations show the error is just too high? Well, you don't scrap the whole design and start over. No way. You iterate. This is where engineering becomes a real art form. As you can see, there are all these different dials you can turn. You can make the tubes longer, change how many times the fluid passes through them, you can tweak the baffle spacing, or even swap which fluid goes in the tubes and which goes in the shell. It's all about fine-tuning.
All of this iteration, all of this adjustment, it leads us to our final and maybe most important idea. The best way to think about this whole process isn't as a straight line, but as this elegant, complex puzzle where you're constantly balancing trade-offs. Every single one of those little adjustments we just talked about, it has a ripple effect. For instance, you could improve heat transfer, but maybe that also increases how much pressure you lose, or it makes the whole thing way more expensive to build. You might pick a design that's easier to maintain, but it costs a fortune up front. The key takeaway here is that there is no single perfect design. There is only the best design for a very specific set of constraints, including the budget.
So at the end of the day, designing a heat exchanger is really a masterclass in balancing these competing priorities. You've got the hard science of heat transfer, you've got the economics of manufacturing, and you've got the simple practicality of whether someone can actually use and maintain this thing. A truly great engineer is someone who can find that perfect sweet spot where all of those things meet.
We've just walked through this incredibly careful, deliberate process for designing something for a specific job. But it kind of begs a final question, doesn't it? What happens when a design like this gets pushed to its absolute limits out in the real world? What are the consequences when that careful balance of science, economics, and practicality finally breaks?